This is 4.4b, rules of probability. So we're going to go through a couple things that are common probability. They're not rules really, but they relate to the rules of probability. And we're going to go through a couple things of how to calculate different probabilities without having to make a factor tree every time, basically. So we still have the factor trees, and you're still going to have to use the factor trees at this point, but we're starting to learn things that will move us away from making factor trees every time, just to make answering the questions a little quicker. So we have the fundamental counting principle. This is not actually a probability, so be careful with that. This is not probability, but this is a principle that helps us count outcomes through multiplication, which makes things easier to find probabilities. Okay, so we have a multiple choice quiz, has 5 questions with answer choices A, B, C, D. How many outcomes are there? Okay, so remember, outcomes are whole numbers. Well, probabilities are fractions, decimals, or percents. So make sure you pay attention to the difference there. So whole numbers for outcomes. All right, so we have 5 questions. So I'm going to write 5 blanks. Each blank represents a different question. Okay, and then on each blank, I'm going to tell me how many outcomes I have possible. So I have 4 outcomes for the first, 4 outcomes for the second, and so on, because each one has the answer choices A, B, C, or D. And when I multiply all these together, so I use my calculator, 4 times 4 times 4 times 4 times 4, I get 1,024. I have 1,024 different outcomes possible for a 5-question quiz with only choices A, B, C, or D. So you can see, if you went into a quiz not knowing anything, with 1,024 different outcomes, even with only 5 questions and it's multiple choice, it makes it really hard to just guess. That's why you need to study and know how to answer things. Okay, so example 2. Ordering at a restaurant. So we have 5 types of fries, 7 types of burgers, and 12 types of drinks. How many total outcomes? So we have our blanks first, right? In this case, it was questions. Now we have items. So we have 3 items we're going to buy: fries, burgers, and drinks. 5 fries, 7 burgers, 12 drinks. So we multiply 5 times 7 times 12, and you have 420 different possible combinations or outcomes. Okay, and then we can deal with how many arrangements. Okay, we'll go into some more specifics on this when we talk about permutations and combinations, but you could do this using the fundamental counting principle. So I'm going to arrange the letters A, B, C, or D. So A, B, C, D. I have 4 places because I have 4 letters I'm dealing with. Okay. Notice, do not confuse this with answer choices A, B, C, or D on a multiple choice quiz. This is different. Okay, so I can choose any of the 4 letters if I'm trying to arrange them, right? I can write A, B, C, or D first. Next letter, I've already used one of them, so I only have 3 options. If I'm trying to arrange them, right, I'm using all 4 letters, so once I've used one, I can't use it again. Then I only have 2, and then the last option is only 1. So I have 4 times 3 times 2 times 1, which is 24 different arrangements. And when we talk about permutations, you'll actually see that again. Okay, so now we're going to use the counting principle to not just answer outcomes, but now we're going to find probabilities. So notice the difference in the question, where before we were doing outcomes and all the arrangements are how many outcomes, just with order mattering. You have how many outcomes with burgers, how many outcomes. Now we have what is the probability. So what is the probability if I have 3 face cards with replacement? Remember, replacement means we put it back. So I'm going to use the counting principle still. So I have 3 face cards. Okay, we went over the cards. Notice you need to know the cards. Okay, I know there are 12 face cards out of the 52 total cards. Okay, and then with replacement, meaning I put it back, shuffle the deck, so when I draw the next card, I have 12 face cards out of 52. Do it again, and I get 12 face cards out of 52. So what is the probability that every single draw of those 3 with putting it back and shuffling up. I multiply these, use a calculator. I'm just going to use the decimal. Okay, so it ends up as 0.012, which I don't like to just have decimal. Percents make more sense in my head, so I like to convert the decimal to percent. And we get 1.2%. It's only a 1.2% chance if you drew a card, shuffled it, drew a card, shuffled it, drew a card, that all 3 of them would be face cards. And now let's do the similar thing, probability still, but with non-face cards. Still with replacement, meaning we put the card back. So non-face cards, there are 12 face cards. That means there are 40 non-face cards. So it's 40 out of 52 for the first card, and then 40 out of 52 for the second card, since I'm replacing it, putting it back and shuffling. And we get 4 of those. Okay, so I multiply, and I get 0.350, rounding to the 3rd decimal place, and I get 35.0%. It's actually a lot smaller than a lot of people think logically, because 40 out of 52 seems very likely, but it has to happen 4 times in a row, which means we're really decreasing that probability each time. So 35% chance if I did 4 card draws with shuffling in between, that they would all be non-face cards, so ace through 10, non-face cards. All right, example 6, we're throwing you for a loop. It's without replacement now. Okay, what is the probability that I'm going to draw an ace, then the 2 of clubs, without replacement? Okay, so ace, the first card, without replacement doesn't matter for the first card, right? I have a full deck of cards at this point. There's 4 aces in my deck of cards out of the 52. Done. 4 out of 52. The second card, though, I've drawn a card. So we don't know exactly what card it is, but we're going to assume it's an ace because that's the goal. That's the thing we're trying to calculate. So we're going to assume I drew an ace. So I set it aside. Well, now I only have 51 cards in the deck. I didn't put it back. And I want the next card to be specifically the 2 of clubs. There is only 1 2 of clubs in the deck. So I multiply. I use my calculator, so I get 0.002. Move the decimal twice, and I get 0.2%. Very, very small probability, which most people could guess. What is the probability of getting exactly an ace and then exactly the 2 of clubs, the next draw? I mean, even without replacement, which decreases the number of cards, I mean, it's a really small probability. Okay, we're going to talk about factorials. We don't use factorials too much because we have calculators, but they're a thing that come up a lot in probability, so we don't want you to leave this class without having experienced a factorial, basically, and doing some things with factorials. Okay, so 3 factorial. A factorial takes the number and counts down, so 3, 2, 1, and multiplies all of those numbers. So 3 times 2 times 1 is 6. That is 3 factorial. If you typed it in your calculator, and yes, you have a factorial button, you would get 6. I notice it's not just like 3. We're not really excited about 3. It actually means something mathematically. 3 times 2 times 1. Okay, we can deal with some things. So if I had a smaller value here, I have on the top 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. If you know how to use a calculator, you could actually type this one in and it would tell you the answer. And it would work. The problem is, once we get to bigger numbers, if you notice my next example, once we get to bigger numbers, it actually doesn't work on the calculator. The calculator can't handle that big of a number. Okay, we don't want to deal with all of this stuff. So we need to simplify things. So we're going to learn how to simplify right here, right? 5, 4, 3, 2, and 1 all simplify, right? If it's the same on the top and bottom, they simplify to 1. 5 divided by 5 is 1. 4 divided by 4 is 1, and so on. And so I'm actually left with just 7 times 6, which is 42. That is that fraction simplified. But I want to point out there's an easier way to do this. We just need to match one of the factorials. So whichever the smaller factorial is, in this case the 5 factorial, I just need to write out 7 times 6 times 5 factorial. And notice the same thing happens because at that point they're going to line up 5, 4, 3, 2, 1, 0. So we can actually simplify factorials. 5 factorial divided by 5 factorial is 1, and we're left with the same answer. Okay, that is a skill that's nice to have when dealing with factorials, like this one. So I'm not going to write out the 104 factorial, that's the smaller one. I'm going to write out the bottom part here, 106 factorial. So 106 times 105 until I get to 104. And then I just write factorial. Because I know from this point on, they will match. So I end up with those two simplifying. Please remember, you always have at least a 1 left, right? 104 divided by 104 is 1. So it's 1 over 106 times 105, which is 11,130. And I could leave it like that, or you can divide and get the decimal percent, whatever you want. Okay, so nice skill to have dealing with factorials. Where we see factorials is with permutations and combinations. So next thing we're going to talk about is permutations. All right, so you got to have some things that you understand here. Permutation, the order matters. So 1 and then a 2 is different than a 2 and then a 1. The order of the values matter. Okay, so key words here, orders or arrangements. Remember when I talked about permutations, when we talked about the arrangements on example 3, you could have used this. Okay, and there's a formula here. We're not actually going to use it because we're going to use this piece because our calculators can do this. But I'm going to talk about it. So this has the factorials in it. So it says how many arrangements of the letters A, B, C are there? Okay, so to use this thing, we need n, which is the number of options. So how many options do we have? 1, 2, 3. We have 3 options in this case because we have 3 letters we're dealing with. And we also need R. R is the number of spots. The number of spots we're going to fill. In this case, we're going to arrange all 3 letters. So we have the same number of options and spots. Okay, so 3 is N and 3 is R. So we would write out 3P3, which we could use this thing. It'd be 3 factorial over 3 minus 3 factorial, which actually is an important thing to talk about. That's why I'm doing this. Because a lot of people are like, well, 0 factorial must be 0, right? 3 minus 3 is 0, so it's 0 factorial. And the weird thing is, this is actually a 1. So 3 factorial is 3 times 2 times 1. 0 factorial is 1. So you end up with 6. Okay, which we could see that. But we want to practice, and I want you to actually see the 6 arrangements. So we have A, and then B, and then C. We also have A, and then C, and then B. Remember, order matters with a permutation. We have B, and then A, and then C. And then you have B, and then C, and then A. You have C, and then A, and then B. And finally C, and then B, and then A. Right? 1, 2, 3, 4, 5, 6. Those are our 6 possible ways we could arrange them. And so you can see that's 3P3 is a lot easier to work with. Okay, so I get 3P3. So this, you can use your calculator for this. A lot of people don't know that they can use their calculator from this. So if you get out your calculator, you're looking for probability section for a lot of people. It might say prob, and then you would usually type in 3, and then NPR, and then 3. So that tells you the N comes first, then the NPR, then the R comes second, and you hit enter, and you get your answer. Some calculators, you have to do the NPR first, and then you hit the N, and then the R after that. So it depends on your calculator, but no matter what, you should get out the answer of 6. So example 7 says we have 10 flag options. how many arrangements of 6 of the flags can I make? So we're not going to use all of them this time. So the number of options is n, the spots is r. So I have 10 flags I'm putting into 6 spots. So this is 10p6. The bigger number should always be first. If it is not first, you did something wrong. Okay, so we type this in, 10 NPR6 or NPR10, then 6, whatever your calculator uses, 151,200. A lot of possible arrangements, 151,200 arrangements. We're not going to write out all these because that would take forever. Okay, then, so that's permutation. Now we have combinations. If you probably could have figured out, order doesn't matter. So we don't care about the order of them. We just want to know how many different groups we can make. So the first, it's groups or committees. If you see groups or committees, the order doesn't matter, right? If you are selected, you are on the committee or in the group, right? Doesn't matter what order you're selected, as long as you're selected, it's good. Okay, so that's where an order doesn't matter. So this first question is not very exciting because it says how many groups can we make with the letters A, B, or C? I mean, think about it. If I'm using all of them, I can make one group. It has an A and a B and a C in it. That's it. So there's only one group. I forgot to type out the formula. NCR is n factorial over n minus r factorial, r factorial. I'm not even going to use it this time because we're just going to jump right into using the combinations though, but there is a formula. So in this case, n and r represent the same thing, it's just a c in between. So n is the number of options, r is the number of spots. So in this case, we have 3 options with 3 spots to fill. And if you use the same probability thing, you'd notice it's 3C3, which is 1. I have 1 possible group to make. Like I said, not very exciting. But we could say, what if I had 3 students chosen from 8 to create a committee? How many different committees can I make? So I only have 3 spots, that's R, and 8 students to choose from, that's N. So how many different groups can I make? Remember, the order doesn't matter, so it's going to be a smaller number usually. If order matters, you're going to have a larger number. Order not mattering, you have a smaller number. So this is 8C3. I have 8 students, 3 spots to fill, and I get 56 different values. And remember, n is always the bigger number. If you flip these, if that's 3 in front and it's smaller than the other one, you made a mistake. The first number is always the bigger number. Sometimes they are the same, but if they're not, it's always bigger. All right, example 9. So this does not relate to combinations and permutations. This is just one last thing to talk about. Lots of examples, lots of different ways you're going to see probabilities. So you want to interact with all of these different things. So it says, what if we're getting exactly 2 3s? So if I rolled 4 dice, I want the probability of getting exactly 2 of them that read 3s. Okay. So this is more complicated now. I want exactly 2 3s. So if I think about it, I have dice, right? A lot of people can figure out this part right here, the first 4 things. I want a 3, and then not a 3, and then not a 3, right? I want 2 of them that have a 3, and 2 of them that don't have a 3. So I have a 1/6 chance of getting a 3. Most people know that. 1 out of the 6 options is a 3. The not 3s are a little confusing. So not 3s means it's not a 3. So 1, 2, 4, 5, 6. There's 5 out of the 6 options. As long as I'm anything else, that's good. And so most people would just multiply that and get it. But the problem is we have different combinations here, right? Talk about order doesn't matter for combinations, which people get confused about when I use combinations right here. But remember that combinations are different ways of combining it, okay? So we need to figure out, well, how many different ways can I make 4 dice have 2 3s? So I have 4 options because I have 4 dice, but I only have 2 spots for the 3s. So how many different ways can I have 4 dice make 2 3s? The order doesn't matter here because we don't care what order we make those 2 3s. We just have to make those 4 dice have exactly 2 3s. That's why we use combinations. I understand that if you look at this, yes, the order matters, right? If I had not a 3, then a 3, not a 3, then a 3, that doesn't matter. But when we're talking about the combinations here, what the number we're multiplying by is just how many ways can I get those 4 dice to have exactly 2 3s. Doesn't matter the order of them. Okay, so be careful about that. So this is the number of ways we can make this roll happen. So it's one extra step that's thrown in here when we have a little bit more complicated of a probability. So you'd actually type this in, 1 divided by 6 times 1 divided by 6 and so on, and then times 4 in CR2, and you get 11.6%. Going straight to percent, I just moved the decimal twice. I got my calculator, looked at it, moved the decimal twice, 11.6%. So there's 11.6% probability that if I rolled 4 dice, exactly 2 of them would be a 3. Okay, so you have quite a few things we went over here. So 3-sentence summary, write it out.